Is it possible to figure out the last digit of 8 to the 1001 power, even though that number is way bigger than the number of atoms in the observable universe, and even though it's way bigger than a Google? Yes, you can, even without technology. Let me show you how. In fact, let me show you two ways of doing this problem. The simpler way is based on pattern recognition, and the fancier way is based on properties of modular arithmetic. It's going to be helpful to write powers of 8 as powers of 2. 8 to the first power is 2 to the third power, 2 times 2 times 2. 8 to the second power is, of course, 64. That's the same as 2 to the sixth power. Why? Because 8 is 2 to the third power, and we are squaring that. And in this kind of context, you multiply those exponents. 3 times 2 is 6. Continuing, 8 to the third power is 2 to the third power. Multiply those exponents and get 2 to the ninth power. 8 to the fourth power is 2 to the third power to the fourth power. Multiply those exponents and get 2 to the 12th power. 8 to the fifth power is 2 to the third power to the fifth power. Multiply those exponents and get 2 to the 15th power. The pattern continues. What we see is that these powers of 8 are also powers of 2. In fact, multiply the given power of 8 by 3 to get the corresponding power of 2. This is useful because it's relatively easy to figure out powers of 2 in your head. Let's go ahead and make a chart. We'll have one row for the values of n, the power of 2, going from 1, 2, 3, 4, etc. Let's go up to, well, n equals 15 here. 7, 8, 9, 10, 11, 12, 13, 14, 15. Then we'll write the corresponding power of 2, 2 to the n power. We just need to keep doubling each time. 2 to the first power is 2. 2 squared is 4. Just double, 2 to 4. Double again to get 2 to the third power, which is 8. Double again to get 2 to the fourth power, which is 16, etc. Then I get 32, 64, 128, 256, 512. 2 to the 10th power is 1024, right? It's kind of fun to do these in your head. Then I get 2048, 4096. It's starting to get a little harder here. 2 to the 13th power will be 8192. 2 to the 14th power will be 16,384. And I'm almost out of room here. 2 to the 15th power, let's put it down here, will be 32,768. The powers of 8 are every third one. 8 to the first power is 8. That's the same as 2 to the third power. 8 to the second power is 64. That's the same as 2 to the sixth power. Keep going by 3. 8 to the third power must be 512. You can check it on your calculator. The same as 2 to the ninth power. Go 3 more. 8 to the fourth power must be 4096. The same as 2 to the 12th power. And 8 to the fifth power must be 32,768. The same as 2 to the 15th power. Now look at the patterns of these last digits. 8 is its own last digit. 64 has a last digit of 4. 512 has a last digit of 2. 4096 has a last digit of 6. 32,768 has a last digit of 8. What do we see here? The last digits are 8, 4, 2, 6, 8. Does that mean the pattern continues? Well, I'm not going to prove it, but it does. It would continue. 8, 4, 2, 6, 8. 8, 4, 2, 6, 8. 8, 4, 2, 6, 8. Every fourth power of 8 repeats with the last digit. The key thing to note here to finish the problem is that, for example, 5, this power of 8, is one more than a multiple of 4 and gives us a last digit of 8. Just like 1001, this power is one more than a multiple of 4. Therefore, its last digit must be the same. It must be an 8. The last digit of 8 to the 1001 power equals 8. In fact, there's really nothing special about 1001. This would be the same last digit for 8 to the 1,000,001 or 1,000,000,001. As long as this power is one more than a multiple of 4, the last digit will be 8. What now is the fancy way to do this with modular arithmetic? What we're going to do is we're going to take 8 to the 1001 power and we're going to mod it by 5. What does that mean? It means we're going to figure out the remainder that we get when we divide 8 to the 1001 by 5. Now again, 8 to the 1001 power is a humongous number. I don't want to write it down. So I need some other method to help me figure out what this is. We start this method in the same way we did up here, except we use that 1001 power as is. Write 8 as 2 to the third power. That's getting raised to the 1001 power. We're going to again mod by 5, which means we want to find the remainder when we divide this by 5. Now go ahead and multiply those exponents. This is the same as 2 to the 3003 mod 5. Now realize that 3003 is 3 more than a multiple of 4. I'm going to write 3003 as 750 times 4 plus 3, and then I can use a property of exponents, a couple properties of exponents in fact, to write this ultimately as 2 to the 4th to the 750th power times 2 to the 3rd mod 5. I used a couple properties of exponents there. Of course, 2 to the 4th is 16, so I get 16 to the 750 times 2 to the 3rd, which of course is 8. It doesn't really seem like we're getting anywhere, but now is where you do the key trick. When performing modular arithmetic, you can mod first. You can mod these individual numbers, 16 and 8, by 5. What's the remainder when you take 16 and divide it by 5? It's 1. You can replace this 16 with a 1. And 1 to any power is 1. Again, 2 to the 3rd power is 8. What's the remainder when you divide 8 by 5? It's 3. I can replace the 8 with a 3. The answer is 3. How is this helpful? We're saying that when you take 8 to the 1001 power and divide by 5, you get a remainder of 3. Now 8 to the 1001 power has got to be an even number. Its last digit has to be a 0, 2, 4, 6, or 8. The only way I'm going to get a remainder of 3 when I divide that by 5 is if that last digit is 8. Pretty amazing, huh? In case you don't believe me, you can go to Wolfram Alpha and see all the digits of 8 to the 1001 power. Here they are. If we show more digits, and even more digits, we will see, there are no more dot dot dots, a last digit of 8. Notice a decimal approximation is 9.8 times 10 to the 903rd power. This number is really humongous. In fact, the Wolfram program Mathematica will do even bigger numbers. For example, 8 to the 1,000,001 power. Here it is, you ready? There it is. What's its last digit? It is indeed an 8. Thanks for watching.